Okay, so the next NMR problem that we're going to do is quite a bit more difficult than the first three. If you look up at the top left, you'll see the molecular formula of the molecule C7H14O2, and on the bottom you'll see the NMR spectrum. We're going to zoom in on the spectrum in a moment, but for the beginning, let's take a look at the molecular formula and try to tweeze out a little bit of information from that. So the first thing you always want to do when you're given the molecular formula is to try to calculate the degrees of unsaturation. This is going to yield very useful data that we can play around with later. So just to remind everyone, the du is going to tell you either the number of pi bonds in your molecule and or the number of rings in your molecule. Okay. However, the du does not differentiate between how many of one versus the other you have. So just to remind you, if you don't have the equation ready to go, this is the equation for the du. So the number of carbon atoms minus the number of hydrogen atoms over 2 minus the number of halogens over 2 plus the number of nitrogens over 2 plus 1. Okay, so I'm just going to pause the video and have you calculate the du real quick, and then you can unpause it and make sure your math is right. Okay, so you should have gotten a du of 1, and if you didn't, just double check your math. It's probably just a little small error somewhere along the way. But our du for this molecule is going to be 1. So what this is telling you is that your molecule has either 1 pi bond or 1 ring within the molecule. Okay, so now that we have our du, let's go ahead and zoom in on the spectrum in the region that actually will give us some information. Okay, so I'm going to keep the molecular formula up top on the left, and now that we've zoomed in, it's going to be a little bit easier to tweeze apart a little bit more accurate splitting patterns for each one of these guys. So compared to the problems that we've done before, these splitting patterns are a little bit more complex. Okay, so the first thing I would suggest you do is take these splitting patterns and convert them to tablature. So whenever you're actually trying to figure out structure, it's going to be a lot easier just to reference numbers versus looking at pictures. So I'll just start from a ppm of 0 and work my way downfield from there. And I'm also going to label each carbon or each peak as I go along. So let's call this peak A. We'll have a peak B, C, D, and E. And peak A is going to show up at around 1.0 ppm. It's going to have an integration of 3. And it's going to have a splitting of around 3. So this is going to be a triplet. So T for triplet. The next peak shows up at around 1.4. It's going to be a doublet, and it's going to integrate to 6. So the ppm is 1.4. It's going to integrate to 6, and it's going to be a doublet. The next peak, peak C, shows up at 1.5, and here's the zoom in for that region. So we'll just say 1.5. The integration is going to be 2, and the number of peaks in this overall signal is going to be 1, 2, 3, 4, 5, 6. So there are 6 peaks. So we have a specific name for this. So the signal at 1.5 that gives an integration of 2 is going to be referred to as a sextet. Okay. The next peak shows up at 2.3. It's going to have an integration of 2 and a splitting pattern of 3, or a triplet. So again, 2.3. It's going to have an integration of 2, and it's going to be a triplet. And then the final peak, peak E, is going to show up at 4.3, and here's the zoom in of that region right here. So the signal at 4.3 is going to have an integration of 1, and a 1, 2, 3, 4, 5, 6, 7, a 7 peak splitting pattern. So again, the shift is 4.3, integration of 1, and overall splitting pattern of 7. This has a special name called a septet. Okay, so The next thing we want to keep in mind is the overall DU for this molecule. So the overall DU was, just to remind you, was 1. The next thing we're going to take a look at is the proton count. So remember that all of these integrations are relative. They might not be absolutely correct. So you always want to make sure that these integrations actually add up to the real number of protons in your molecule. So we have 1, 2, 3, 4, 5, 11, 14. So we have a total hydrogen count of 14, total hydrogen count up top of 14. So the proton count seems to work out just fine. Okay, so now that we've made sure that the proton count works out, what we're going to do now is we're just going to get rid of the physical spectrum and here on out just reference the tablature data. So we're just going to get rid of that. And the first thing that we want to do is hypothesize likely carbon-hydrogen frameworks. So all that we're really doing here is saying of multiple hypotheses that we could potentially present, we're going to go with the easiest one. And the easiest one is going to be the hypothesis where we have to explain the least amount of stuff. So the less amount of work that we have to do, the better. Okay, so we're just going to simplify it in that way. So the first peak, peak A, is going to integrate to 3. Most likely explanation is a CH3. Next peak, peak B, integrates to a 6. And here, this is where we really have to make a decision. So we could have two possible explanations here. We could have two CH3 groups, or we could also have 3 CH2 groups. So either one is just as likely in this stage of the game, but since we said we're going to go with the simplest explanation, and the simplest explanation being the one that we have to explain the least amount of data, the easiest one to explain is going to be the 2 CH3 groups. So this could be wrong, but for now let's just go with it, and if it turns out to be wrong, we can always come back and go with the other scenario of having 3 CH2 groups. Okay, so next one along the line is going to be the peak, or the C peak that integrates to 2, so this is more than likely going to be a CH2, and then the next one along the line is going to be the D peak, which is again probably going to be a CH2 because we have an integration of 2, and then finally peak E shows up as an integration of 1, so we're more than likely going to have a CH group. Okay. So the next thing that you want to do is check your carbon count. So after we've hypothesized likely carbon-hydrogen frameworks, we want to make sure that we're not leaving anything out. So if we go down the line, we've explained 1, 2, 3, 4, 5, 6 carbons. And if you look back up at your formula, we have 7 carbons that are actually in the molecule. So at this point, it might seem like our initial hypothesis was wrong, and we might actually have 3 CH2s, which is a possibility. Another explanation, though, is that we could theoretically have a 7th carbon that simply doesn't have any hydrogens attached to it. And if that's the case, there would be some kind of scenario where we could have this carbon with 4 groups that are not hydrogens, that are not a hydrogen, or we could potentially have, a carbon with a double bond, which might work out since we have a DU of 1. So the next thing is we're going to take a look at chemical shifts. And chemical shifts give quite a bit of information that can be very, very helpful. So along this data table, the ppm shift that actually stands out very, very much to me is this peak at 4.3. And if we look at our data table here, the type of peak that shows up between 4.0 or 4.5 and 2.5 is a hydrogen that is geminal to an oxygen or a nitrogen or a halogen. So if we take a look at this CH, a very likely kind of framework that we could talk about is if not only do we have a hydrogen here, but we also have oxygen, which makes sense since our original molecular formula has 2 oxygens attached. So that seems to, explain that chemical shift. We've already explained the integration. Next thing along the line is to try to explain the septet. So the septet means that if we look at our n plus 1 equation, so n plus 1 is going to equal 7, n is going to equal 6, which means that there are 6 adjacent hydrogens to this hydrogen. Okay, so let's go ahead and label this guy. This guy is hydrogen E. And so if we're going to have 6 adjacent vicinal hydrogens, the easiest way to explain that would be to have two CH3 groups. So CH3, CH3. So there's 3 hydrogens here, 3 hydrogens here. That's 6. That seems to work out right there. So we seem to have explained shift, integration, and splitting for this one particular CH. So CHE. So let's go ahead and strike that one off. So we've explained E. So let's see if we can actually find a peak in our NMR spectrum that might correlate to these two CH3 groups, and that would be very convenient if there was. So let's look for two CH3 groups that are equivalent. So at this point, it seems that these two CH3 groups are going to be chemically equivalent. So if you look along the table, we have two CH3 groups here that we initially hypothesized. So let's see what kind of data we can get from that. So shift of 1.4, that's somewhere next to an allylic or potentially next to a carbonyl group, or it's right also on the edge of a saturated group. So these two CH3s are in kind of a saturated region. We have a little bit of an electronegative pull from the oxygen, so it's probably pushing it a little bit farther downfield than it normally would be. So that seems plausible. The next thing is the integration. So 6 protons here, so we have 1, 2, 3, 4, 5, 6. That seems to work out. And so then the next thing is the splitting pattern, so a doublet. So if we look at these these CH3s right here, the only vicinal proton that we have is proton E. So for this guy, N is going to equal 1, and so 1 plus 1 is going to equal 2. So that should show up as a doublet. And it does seem that it shows up as a doublet. So it seems pretty likely at this point that these two CH3 groups are going to be protons B. Okay, so it seems that we've kind of explained these two CH3s, so we'll go ahead and strike all of these out. And we're also going to go up above and acknowledge the fact that we've deleted one of the oxygens that we have to explain, and we have to also acknowledge that there's still one more oxygen that we still need to explain away. Okay, so that's one extra oxygen. Alright, so what we're going to do now is try to tie all the pieces together. So we have 1, 2, 3, 4, 5 pieces of data to try to, pull together. What we're going to do is try to now explain what potentially could be a quaternary carbon, or a carbon that just doesn't have any hydrogens attached to it. So keeping in mind the degree of unsaturation, as well as the fact that there is one extra oxygen in our molecule that we still haven't accounted for, it seems like the easiest way to explain this guy away is to make this a carbonyl group. So let's just say we'll make a carbonyl group, and I'm just going to arbitrarily attach it to the oxygen. So at this point, this carbon is now this carbon, so we've used that guy up. It's no longer a puzzle piece. We've also used up an oxygen, so we've used that oxygen up. It's no longer a puzzle piece. And we've also explained away the singular degree of unsaturation that we have in the molecule. Okay, so now we've taken care of 3 pieces of data almost simultaneously. So now all we have to do is really explain a CH2, a CH2, and a CH3. So since we've started to introduce this carbonyl group, this is an ester group, we might as well go ahead and start adding carbons to that. So we have to add some kind of carbon. Okay, so the next thing we're going to do is just start adding on CH2s. So let's add on a CH2 here. Okay, so if we had a CH2 here, that could correlate to either protons C or protons D. Okay, so either one could potentially be possible, but if we look at our graph down below, the characteristic ppm shift for a hydrogen that is adjacent to a carbonyl group is around 1.5 to 2.5. It seems like really the only peak that falls very nicely in that region is peak B. So this guy falls at around 2.3, which is right somewhere in the middle, a little bit farther downfield, but still well within the region. So that seems to work out okay for these two protons being proton D. Okay, so they have the right ppm shift, they have the right integration, and so then the only thing we have to take care of is the splitting pattern. So if the protons D were a triplet, that would indicate that N plus 1 is 3, so that means N is equal to 2. So that means that we have 2 vicinal protons to protons D. So if that's the case, it's very simple to draw out. So we have 2 vicinal protons to protons D. So that would explain that triplet. So we'll go ahead and get rid of that. We'll get rid of that. And so now we only have protons C and A to work with. So in the process of explaining away protons D, we hypothesized this extra methylene group, or this extra CH2 group. And this seems to work out really well with the tablature data that we have. We have an extra CH2 here, so that seems to be okay. If that's going to be consistent with the rest of the molecule, though, we need to take a look at the ppm shift. So these CH2s for C has a ppm shift of 1.5, which shows up right at the edge of a saturated molecule, so that, that seems okay. The next thing is the integration, so an integration of 2, that works out. So right now, let's just say that the CH2 is potentially protons set C. So then after that, the only other thing we have to explain is the sextet. So that means N plus 1 equals 6. So N is going to be equal to 5. So that means that for the proton set C, we need to have 5 adjacent vicinal protons. So we already have 2 that are vicinal to C. So that means that we have to have 3 extra protons. So that was easily explained by a CH3 here. So now proton set C has 1, 2, 3, 4, 5 vicinal protons. So N would be 5, N plus 1 would be 6, and that would explain the sextet very, very well. Okay, so it seems like we've explained proton set C. And then the last thing we have to do is take a look at this last methyl group right here, which might, or seems very likely to be this methyl group up here. So let's just make sure that the chemical shift makes sense, integration, and the splitting pattern. So a ppm value of 1 would be in the saturated region. This is definitely in the saturated region, so that makes sense. Integration of 3 hydrogens, that seems to make sense. And then finally, the splitting pattern of a triplet. So that triplet is going to be N plus 1 equals 3. So N is going to be equal to 2. So that means that there should be 2 vicinal protons to proton set A. So let's just say this is proton set A. And so if we look at the vicinal protons, we have 1 here and 1 here. So N would be 2 in this case. So that seems to work out just fine. Splitting pattern makes sense, and we explained away that last proton set A. Okay, so again, proton set B, proton set E, D, C, and A. And if we were going to draw it out, we would have 1, 2, 3, and we would have the carbonyl, oxygen, and then the carbon, the methine, and then we have the 2 CH3s attached. So this would be that molecule if you were going to draw it out